This is our video for Unit 7, Day 2. What we're going to do today is just review so far in the course all the different parent functions we've covered and their properties, and the next couple of days we'll be adding in some more. But before we did that, I just want to go back over all our different parent functions and different transformations we have on those functions. So far in this course we've actually covered 10 different parent functions. So we've covered linear, quadratic, we did exponential and log, and then we did 6 different trig functions. We did sine, cosine, and tangent, and the reciprocal functions, cosecant, secant, and cotangent. So I just want to go through so you have these all in one place, all different shapes for the graph, domain and range, different properties of the function, and when there are transformations, where those go in the function. So first one we'll go over is our linear function, which has parent function y equals x. So our graph for the linear function is a line. The parent function has slope of 1, y-intercept 0. Domain and range are both going to be all real numbers for linear function. So these are not going to change no matter what transformation we put on the function. We'll always have our domain and range for all real numbers for linear function. Transformations on a linear function we always interpret as slope and y-intercept. So we can always work a linear equation out to this form. Mx plus b. In this form, m, the coefficient on x, that's the slope. And b gives you the y-intercept. But no matter what we change our slope or y-intercept to, that's not going to change our domain and range. So that's just a snapshot of everything we covered with linear functions. So the next function we covered was a quadratic. Quadratic second degree apparent function is y equals x squared. Here's the shape of the graph. It's a parabola. For a quadratic function, our domain is all real numbers. For the parent function, the range, c starts at 0 and includes every number above 0, so 0 to infinity. We have transformations on a quadratic function. It's in what's called the vertex form. So that's a x minus h squared plus k. So the squared, that's what makes it a quadratic function. So when we apply these transformations to the function, that will not change the domain. The domain for quadratic will always be all real numbers. The range will change with transformations. If we reflect over the x-axis, or if we shift vertically up or down, that's going to change our range. So we're never going to change our domain for quadratic, but the range will change depending on what kind of transformations we have going on with the function. So that's everything really with quadratic we talked about with the graph. Next one is our exponential function, which is really, there's two different types of exponential functions. So our parent form, basic form is y equals b to the x. So b is the base. That's part of the parent function. There's a whole bunch of different types of exponential functions. But there's two main types of exponential functions. If b is bigger than 1, that's the exponential growth function. The graph is growing as we go out to infinity. If b is a proper fraction or decimal, then it's a decay function. So the properties of those two functions are very similar. The only difference is growth function is increasing, decay function is decreasing. So for the domain, again, it's going to be all real numbers. Or we can put any kind of number in as an exponent. The range is what's different for these. For both of these, we have a horizontal asymptote along the x-axis. Right, that's along the x-axis, which is the same as the line y equals 0. So it's closer and closer to that line, never crosses. Same thing, growth and decay. So our range is from 0 to infinity, but not including 0. So if transformations on the exponential function, form will look like this. A, b to the x minus h, with h the horizontal shift up in the exponent where the x is, plus k. Important note for these transformations on the exponential function that b is part of the parent function. So it's not a transformation. Right, so whatever number is in the base is not a transformation, that's just part of the parent function. And we add these transformations to the exponential function, will not change our domain. So the domain will not change. But we can change the range if we shift it up or down or reflect over the x-axis. That will change the range for the function. So we add transformations in, that's going to change our range, but our domain will always stay the same for exponential function. So our next function is going to be the inverse of the exponential function, that's the log function. So parent function is a form log base b of x. So this is the inverse, so it has opposite domain and range of the exponential function. So instead of a horizontal asymptote at y equals 0, we have vertical asymptote at x equals 0. Our graph is reflected over the line y equals x. So here the domain for this function is the same as the range for the exponential function. 0 to infinity. Right, not including 0. 0 is where we have our vertical asymptote. Vertical asymptote x equals 0, same thing as vertical asymptote along the y-axis. Right, it's another way of saying x equals 0 is not in the domain of the function. The range which is the same as the domain for exponential since they're inverse, and that's all real numbers. Go down to negative infinity, the fourth quadrant along the asymptote, and then the first quadrant will keep going and extend towards positive infinity. Let's have our transformations on the log function. I have a log base b, x minus h will be in the argument of the log in the parentheses, and then plus k out at the end. So with these transformations, the range will not change. But the domain will change. If we shift it left or right, that's going to move that vertical asymptote and change the domain of the function. So a couple other important things to remember with log functions is there's two log functions we can actually see on the calculator. That's common log, and that's base 10. And there's natural log, and that's base e. And get e on your calculator, that's second, and then divide. So now we're going to get into our trig functions, our 6 trig functions. So first one was our sine function. Parent graph y equals sine x. Remember, this follows that same 5-point pattern starting from 0. Goes 0 up to max, back to 0, down to min, and then back up to 0. So again, period of 2 pi, the pattern will continue to repeat itself. Zero, max, 0, min, and 0. And there's one period of our sine function. From that we can look at some of our properties. So domain for a sine function is going to be all real numbers. So you can put in any number into your calculator, you can put in for sine, and you'll get a number back. The range, all values for sine are between -1 and 1. So we apply transformations to the sine function. This one has one extra piece that the other functions haven't had so far. And that's that frequency, which is like a horizontal stretcher, shrink. Remember, to identify what the phase shift actually is, the horizontal shift actually is, we have to factor out that frequency. So it has to be written in this form, the argument of the sine function, in order to see what the phase shift is. So when we apply these transformations, that will not change the domain for the sine function. Always be all real numbers, but the range will change. Those properties for our sine function. Next one we did was our cosine function, which is very similar. I followed a different pattern though. Cosine starts at a max, down through 0, down to min, back up to 0, and back to a max. So period is still the same, 2 pi. But the only thing's different is our pattern. We start at a maximum, 0, minimum, 0, maximum. So domain and range are going to be the same as they were for the sine function. All real numbers we can put into the domain. For cosine, you put in an x value, you'll get back a y value. But all those y values, just like for sine, will be between -1 and 1. So transformation is the same form for sine and cosine. A cosine, we have to factor out that frequency so we can see what the phase shift is. And then our vertical shift, our midline, is out at the end. Again, transformations are not going to change the domain on cosine, but they will change the range. If we change amplitude or midline, that's going to move where our maximum and minimum values occur. So next one is our tangent function. So this one's a little bit different. It still follows a pattern, still repeats over a regular cycle, but we have a different pattern. So for this one, the period is only pi. So we graph that period between two asymptotes. That's negative pi over 2 to positive pi over 2, which together gives us a full length of the period, 1 pi. But it helps to see the shape a little better because we're graphing between two asymptotes. So mark off our 1 and -1, and then we just make our shape. So the asymptote comes up from the bottom, crosses through 0, goes up through that A point again, and then back up along the asymptote. So the asymptote, this one has a different kind of domain. For this one, we see we can't use any odd multiples of pi over 2. So pi over 2, negative pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Any odd multiple of pi over 2 is not going to be in the domain. So the way we write that is say x is not equal to pi over 2 times 2k plus 1. Right, 2k plus 1 is odd, and pi over 2 is where our asymptote is. So odd multiple of pi over 2 can't have a value there. For the range, goes down to negative infinity along one side of the asymptote, up to positive infinity along the other side, so our range is all real numbers. So all transformations you could still see on tangent, although you don't see them a lot. You could have all the same transformations that we have with sine and cosine. So a tan, frequency and phase shift has the same idea with tangent. Most of the time with tangent we don't see vertical shift, we don't see phase shift, but we do pretty commonly see at least changes in the frequency and vertical stretch. So when we apply these transformations, that won't change the range for our tangent function, but changing the frequency or applying a phase shift will change the domain. It'll move where those asymptotes are. So last three we have to do are three reciprocal functions. So first one is cotangent. Um, so remember that tangent um, is sine over cosine. Cotangent is reciprocal of tangent, so it's cosine over sine. So the domain for tangent is restricted by where cosine is 0. The domain for cotangent is restricted by zeros for sine. We'll see a similar shape. On your calculator, you have to graph this by graphing either cosine over sine or graphing 1 over tangent, since the calculator only has sine, cosine, and tangent functions. It's just like for tangent, the period for cotangent is pi. So the location for the asymptotes is different for cotangent, as well as the direction of the graph. For cotangent, we have asymptotes anywhere sine is 0, so that's any integer multiple of pi. So asymptote is 0, coming down from the left, crossing through 0, down to the negatives. So it's the same shape, general shape as the tangent function, but this is decreasing instead of increasing like tangent. And then the location of the asymptotes is different. So our range is going to be the same, with the asymptotes goes down to negative infinity on one side, up to positive infinity on the other side of the asymptote. And our domain is going to be a little bit different. For this one, our asymptotes occur at integer multiples of pi. So 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, any integer multiple of pi. We can say pi k. So I have an asymptote there. Transformations on cotangent. Usually you don't see a lot of transformations using this function, but if I did, it'd be the same as for the other trig functions. A cotangent, have our frequency, phase shift, and midline. And same as tangent with these transformations, most likely you'll just see these two change, maybe a phase shift, usually not a lot with the vertical shift, but the range will not change. And the domain will change. If we change the frequency or apply a phase shift to the function. So the last two parent functions to cover, last we've talked about, are secant and cosecant. So secant is a reciprocal function. Secant is a reciprocal function for for cosine. So secant is reciprocal for cosine, then cosecant is reciprocal for sine. So when we graph our secant function, we start by graphing a cosine function. So we just follow our regular pattern. We have max, 0, min, 0, max, and then we transform the graph based on properties of the reciprocal. So anywhere there's a 0, if we take the reciprocal of that, that'd be undefined. We have 0 in the bottom of the fraction, can't divide by 0. So zeros will become vertical asymptotes. Minimums will become maximums. And then maximums will become minimums. That gives us our general shape for secant function. So look at the domain. See, anywhere there's a 0 for the cosine function, we have an asymptote for secant. So x can't be anywhere where cosine is 0. So that happens at any odd multiple of pi over 2. So that's the same as for tangent. So pi over 2 times 2k plus 1. Odd multiples of pi over 2. The range includes everything except for the interval where cosine has value. So it goes from negative infinity up to negative 1, skips that whole middle range, starts back up at 1, and goes out to positive infinity. So we graph transformations for secant. We basically follow that same procedure. We apply those transformations to cosine, and then we flip the graph based on reciprocal properties. So our transformation would be the same as for cosine. We'd have A secant B x minus h plus k. And applying these transformations, both of these could change both the domain and the range. If we shift it left to right, that will change where the asymptotes are. And if we move it up or down, that will change the range. And the last one is cosecant. Which is our reciprocal function for sine. So we graph this same way we graph secant. We start with our reciprocal function, we start with the sine function, and then we flip the graph. So our sine function would go 0, max, 0, min, 0. So same idea for our cosecant function. Anywhere sine is 0, we're going to have an asymptote. Any minimums become maximums, and any maximums become minimums. So we end up with the same exact domain, same exact range as we had for the secant function. It's everything except for that interval between negative 1 and 1. It's negative infinity up to a negative 1, and then start back up at 1 and go to positive infinity. Our domain is restricted by anywhere sine is 0, so that's at any integer multiple of pi. So 1 pi, 2 pi, 3 pi, 4 pi, same as for cotangent. X can't be the integer multiple of pi, so pi k. So transformations, just like for secant, we do apply the transformations to sine and then flip the graph. So you have A cosecant B x minus h plus k. And just like for secant, domain and range can both change when we apply transformations to this graph. So last thing, just generally transformations on any function, what they all do. Just go over this before you work through some practice problems tomorrow in class. So I have A, the function, this argument of the function where x goes, and plus k at the end. So there's three things A can do. So if our actual value for A is bigger than 1, that's a vertical stretch. If that absolute value is smaller than 1, or between 0 and 1, It's going to be vertical shrink. And if we have a negative out front, that's going to be a reflection over the x-axis. Two things H can do. If we see in the argument of the function, we have x minus h. It's going to move the function to the right. And if we see in the function, we have x plus h. That's going to move the function to the left. And last, at the end, we have k can do two things. If it's plus k at the end, it's going to move the function up. And if it's minus k at the end, that's going to move the function down. So tomorrow in class, we'll be working through examples of this. If you want to see some examples online or other videos help you with this, you can search for transformations on functions or parent functions.